Welcome to the demonstration corner. Today we're going to talk about the measurement of some silver-filled epoxy that are small sample size. Of course we can go smaller than that, but this is kind of what we have for demonstration today. So we cast these out of some material. These are approximately radius of 8 millimeters and height of 7.5 millimeters. And we'll need that for input into the software a little later. But before we get into the MP-1 and the use of it for transient plane source method, tradition here is we turn the camera around and show all the instruments that are in our demonstration corner and how they can be used. These instruments are all available for demonstrations and one-on-one training. And this same capability is in our international offices, so Thermtest Asia and Thermtest Europe and in Latin America. So we have this common capability in all of our hubs. So first is our guarded heat flow meter. This follows ASTM E1530 for complex materials, and by complex materials I mean heterogeneous or multi-layered that are non-repeating through the thickness. This is a forced or guarded one-dimensional heat flow, so it measures thermal resistance and thermal conductivity. The temperature range of this is -20 to 300 Celsius. And that follows ASTM E1530. That's a steady state device. This is another steady state device for measuring highly insulative materials or insulative materials and construction materials. This is rock wool. The opening on the HFM 100 model. This follows, by the way, this follows ASTM C518 and the international standards that are equivalent. This opening is 12-inch by 12-inch by up to 4-inch thickness or 100 millimeters thick. There's another model, HFM 50, which is 2-inch opening or 50 millimeters opening, and the other dimensions are 200 by 200. There is the plate temperature on the HFM 100 and HFM 50 are -20 to 75 Celsius. There is a new high temperature HFM 100 which goes from -30 to 110 Celsius plate temperature. As you can see, you insert your material and the plate comes down and you get a steady state condition with a delta T that you create through the instrument. The other option you can add to this is a high thermal conductivity kit that extends the thermal conductivity range up to 2.5 watts per meter Kelvin, which is up around Pyrex and concrete, etc., for thermal resistance and thermal conductivity. The other module you can add to this is direct specific heat. So its native measurement is thermal resistance. It measures the thickness and auto calculates thermal conductivity. You can add specific heat capability to this unit. So if we turn the camera around, normally there is a TPS2, which is our principal transient plane source method or TPS method following ISO 22007-2. That has it's on its way to a trade show. Sorry about that. Its conductivity range is 0.01 to 100 watts per meter Kelvin, and you can extend that up to 500 watts per meter Kelvin. There are plenty of videos and information on our website for the TPS2. It measures thermal conductivity, thermal diffusivity, and volumetric specific heat, ideally for solids, pastes, and powders, and viscous liquids if you need to. For doing viscous liquids and a wide range of viscosities, we have the THWL1 or transient hot wire. This follows ASTM 7896, I believe, for thermal conductivity, thermal diffusivity, and volumetric specific heat of liquids and phase change materials. You can back pressure it so that you're testing, so you can test past boiling points. And this has a integrated temperature control. As it is right now, it's 200 degrees, 10 degrees to 200 degrees. It has inclusion of cooling, and the overall range that you can extend this to is -160 up to 300 Celsius, and back pressures two ranges of 20 bar or 35 bar. This is our mini heat flow meter following ASTM C518. It's for doing small scale insulation by the steady state method, heat flow meter method. So as thin as 2 millimeters thick and as thick as 25 millimeters. The sample size can be as small as 50 millimeters square. So it's a small format heat flow meter. And then our MP2 with primary sensors, transient plane source, transient hot wire, transient line source, and variations of those. That is an economical device, still very accurate with limited ranges that we designed for people with a limited budget. So this is our MP-1. Normally next to here we would have temperature platforms that take advantage of the 4 channels that this allows the user to take advantage of. So the room temperature configuration of this looks like this, and this is actually the MP-1 if you were to acquire the transient plane source method as the primary method for testing. If you don't need the ability to test temperatures, then of course this is your basic configuration. But you can still add multiple sample holders just by adding more of these, so you basically can have 4 instruments from one controller. It's like having 4 instruments running 4 sample holders all together in sequence. The software is broken down into data acquisition and analysis. The data acquisition smartly controls the channels so that you're able to test and take advantage of the multi-channel capability. So every MP-1 comes with that capability. Today what we're going to do again is measure a silver-filled epoxy. We'll use the dimensions I previously mentioned, and I'll go over to the desktop. We'll start entering some of the dimensions, and the Transient, or the iTPS, which is our intelligent addition to the transient plane source method, automates all selections of parameters and analysis. So this is really a demonstration of small materials as well as how the iTPS works and how that automates the method itself. So before we do a sample setup, you see we have 4 sensors. These are some of our sensors. We have smaller and larger, but these are, so I'm going to switch the cameras so you can see a little closer what I'm looking at, but let's go over to the software and start that process. So this is our principal data acquisition software. So we have created 2 software applications for the instrument. This is the main application that controls the instruments and the channels and collection of data. The analysis app is where we import that data for automation of analysis, but also if you want to dive deeper and deeper understanding, that is where we do it. And we'll demonstrate that as well. So this is our general device. Before I do that, as of right now, you can see we only have 1 device connected. If you had more devices, you would see them populated here on all the different channels, but this is just the room temperature setup. So the user, we're going to select the method, which is transient plane source, and we're going to do symmetric, isotropic, and infinite. And we're just going to save this to the desktop. This is your controller, and we're going to do room temperature testing. And here is our location where we put in our information. So we're going to just put epoxy. This is silver-filled epoxy. The sample height is 7.5 millimeters, and the radius is 8 millimeters. I'm going to select port 1. So this unit, the sample holder as it is connected to port 1. And then this is where the intelligent iTPS, or the iTPS suggests the sensor. So from the dimensions that we've input from the sample, the sensor is automatically selected. And so it's selected very much on the required distance between the edge of the sensor to the edge of the sample. There's a minimum amount of penetration depth that each sample and or combination of sensor and sample needs. This is all automated for that. Now if you want to manually select sensors because you're an expert user and you want to look at let's say heterogeneity of your sample, and you want to look at different probing depths from small to large, you could certainly do that. But for ideal conditions, the iTPS does a nice job of selecting the sensor automatically. So we're going to check the resistance. That just makes sure that we have not set the sensor up yet. So I've tried to check the resistance when there's no sensor inserted, which is, this should fail and get an error, of course. So it's while you're doing live things, this is a good demonstration of the software in this particular case. So I'm going to go to camera 2. And we'll set the sensor up and check the resistance again. So as you can see here, we have 4 diameters. This is 20 millimeter diameter, 12.8, 6.4 and 4 millimeters diameter. Of course, we could probably use even the smaller one, but the software suggested ideally the 6.4 millimeters diameter because of we want to penetrate as much of the sample as possible, but not penetrate past the dimensions. So ideally, the 6.4 millimeters diameter is the best suited. So we're just going to select that guy. You can see that the transient plane source sensor has 4 contact points, 2 provide current and 2 read electrical resistance. So we'll just move these other sensors aside. And I'm going to pull the camera in a little closer. And we're going to insert those into the adapter, face down. There's 4 contact points that are underneath that opening. And we're going to move that plate up and down by turning that screw. And there's a window in the back that tells you if you fully insert it. And that pretty much automates the selection. It pretty much simplifies the insertion of sensor. So once it's in there, you can see it in the back. Let me pull this up so you can see this. This will be a little shaky, but I think it's good to see it. So you can see where your sensor is in relation to the contacts. And then we'll just squeeze it down. That creates electrical contact between the contact points. We're going to run symmetric, which would mean a sample on top and on bottom. But if you wanted to run asymmetric or single-sided, your configuration would be the included piece of XPS. You would lower your sensor, and then your configuration would be like that. So we're going to do symmetric, which is sample on top and bottom. So we're going to lower the height of the sensor to match the height of the sample. So the sensor's sitting relaxed. Then we're going to put our matching piece on top and use a disc that comes with the instrument to protect the surface of your sample. Then we're going to lower the top bar, and that gets us close, and we just fine-tune the compression by turning that. Oh, I guess. And that's your sample setup. So go back to software and run check sensor. In this case, it should be okay, because we actually have a sensor inserted. So this also is it's another way of checking, like by chance, if I were to have selected the wrong sensor from my available sensors, this would give you a warning saying, even though there's a resistance, that resistance doesn't match the range of that diameter that it should be. The temperature is automatically taken from the adapter. There's a temperature sensor inside the adapter. So if you have this sensor on the bench or in a chamber, it will record that temperature automatically. And if you want to run temperatures with this sample holder gives you somewhat more flexibility with sample size. It can take a sample of 100 millimeters square by up to 50 millimeters thick per each half. So of course that's quite a bit of flexibility. If you want to use that in an oven you already have because you're on budget, the adapter and the sample holder that comes with that sample holder is good up to 80 Celsius and down to minus 75 Celsius. We can upgrade the adapter, the one that you saw me insert the sensor into, to 300 degrees. So essentially you can use your own oven, and we have ovens that are larger that allow you to insert that sample holder inside of it, that are all fully automated. But so you can use the ones off the shelf that are available for that sample holder, as well as maybe one you have in your lab. Both are options. So once we've entered the dimensions and selected our sensor size, which again is fully automated, we can go to what is the thermal conductivity range of this material. This is in the medium scale, and we can run our iTPS function. So by clicking that button, this is going to do a measurement automatically that measures a time that will go beyond the available dimensions of the sample. So why we do that, why this does that, is it's looking for the edge. So when you make a measurement longer than what you have available as penetration depth, you're actually affecting the transient. You can see that in your residual patterns. You can actually see it. So instead of the user visually determining that time, the iTPS does it for you. So it measures a time where the heat is staying within the dimensions of the sample, and it's also looking for the time where it goes beyond that. So it's selecting a time that's less than the available penetration depth. So the diversity of time on the MP-1 is anything from 0.25 seconds up to 2,560 seconds. So it's a wide range of time. And of course, that's all based off how big your sample is, how conductive it is. So the smaller the sample is, the more conductive it is, the shorter the time. And the larger, more insulated it is, the longer the time. So everything in between. So this is running based off the dimensions that we input, a time scale that will penetrate beyond the dimensions and give us a time and power based off of those two parameters that we need to set to move on to the schedule to run multiple measurements of the same sample. So what you're seeing here is little gaps in a very long transient. Those gaps are the data from the instrument being dumped to the analysis application all automatically for calculation. So there's a short pulse, and these are not individual measurements. This is one continuous measurement. So we're not starting a measurement and then another one, then another one. The challenge with that, if you did that, you have to wait several minutes between each measurement, because the new measurement you make would affect the other one, and we don't want that. So this is the most efficient way to rapidly get one measurement that gives you time and power based off the available dimensions. How does the unit know the penetration depth? Because it's measuring thermal diffusivity. So one of the outputs of the instrument, besides thermal conductivity, is thermal diffusivity. So from thermal diffusivity, it calculates the penetration depth. So it always knows where the heat that it's providing through the sensor is in relation to your dimensions. So if we close that, here we can run a quick transient. Before I do that, I have introduced a little bit of heat from the iTPS. Normally I would just go to the schedule and run a full automation of, let's say, 5 measurements with the power that the iTPS gave us. But let's wait a moment. The quick transient, what the function of that is if we want to run quick simplified measurements within this window, we can. It gives us a really quick way of looking at data. So I'm going to wait a few moments. While we do that, we can look at the data in the analysis app that we've run previously. So here's the thermal silver-filled epoxy, same sample, that we've measured with the time and power from previous measurement. And the residuals, here's our temperature rise versus time and our drift stability. So with every measurement of time, you get a measurement of drift. So there's a little bit of drift in that, so we could have waited a little bit in between each measurement to allow the heat to dissipate, but that's a very small amount of drift. Ideally, you're looking for a nice random pattern, so that was all done individually. So you can see some of these later ones, the drift isn't too bad. That could also be the room, if there was an air conditioner coming on, so in those cases, you just want to make sure your room is stable. So our residual pattern is good, so we want a nice random scatter. That means that the fitting of the portion for calculation of the data is good quality. And here is our bulk conductivity, thermal diffusivity, and volumetric specific heat for that sample. And then the stats for each row and column. So that's 5 measurements of the same sample. From here, we can export to Excel. So if we want to generate a full report, you just ask, where do you want to save it? And the default program to save is in Excel. So here you can see the different graphs that were associated with just measuring at one temperature. Again, with the MP-1 specifically, we measure the contact resistance between the sensor and the sample. That lets us remove the effects of contact resistance automatically. That's, again, part of the iTPS series that automates the selection of parameters as well as the analysis. So therefore, you don't have to manually select that portion of time, which is common to other methods. Of course, you can. If you want to, you can turn off contact correction, and that will allow you to manually select the time as well. So that's an important part of the MP-1, is both the ability to measure and look at your analysis for deeper understanding, or if you just want to run it automated, you can do that. So I think we've waited a few minutes. So let's go back and run a quick transient. So in our quick transient, there's no recording of drift. Again, this is only meant as a quick measurement of the parameters that the iTPS generated, if you want to do so. There's a lot of confidence in that data, so you really don't have to, but it's nice to show this. This is the event log, so it tells you what is the stage of the measurement. So it's recorded the temperature of the room. It will balance the internal bridge, and then go right into measuring the thermal conductivity. And I think the time it selected was 3 seconds. So it's running the test. There's our transient of temperature rise versus time. You can see it's analyzing. So it will do a certain amount of analyzing right within the data acquisition application, but we of course prefer that to be within the the transient analysis application. But this gives us a look at the quality indicators. So our penetration depth, if you remember, that we're calculating based off of a radius, what the penetration depth is, that's all automatically calculated. Our TCT is 0.55. What that means, that's again the selection of time that auto looks at how far heat is penetrating past the sensor. So if you read the ISO, it's comparing, it wants you rather, with your selection of time, to penetrate at least the equivalent probing depth to the radius of the sensor you're using. And the radius we're using is 3.2 millimeters. So we've probed past 3.2 millimeters from every edge of the sensor. So that would be from each side of the sensor, if the sensor is sitting in the middle of the sample, and the thickness. So those are good indicators. And then our residual pattern is nice and random. So that's what the quick transient is for. So now we can proceed to the schedule window and generate a maybe measurement of 5 with a 10-minute delay at the time the iTPS suggested, and start. So from here, our schedule will be built on the experiment list. Again, this could be populated with a lot of different experiments. I could do another set of experiments on the same channel, but also if you had other types of sensors or other types of, or repeat of the same sample holder on the same unit, you can build many more, rather you can have a lot more volume in your testing just by using those channels and the smart application for scheduling those. So that is the entire setup. You can see the event log is very similar to the quick transient. That will show each measurement with the same type of quality indicators you saw from the quick transient, and then we would open up the application of thermal. And here, if you wanted to shortcut to that transient analysis, here you can see the quick transient we did, and these are the auto parameters. The quick transient we did for that sample, it's calculating. And this is the series from the past measurements we did that showed good residuals and bulk properties from that same sample. So that concludes the demonstration. We'll allow, I want to just select that so you can see the conductivity. So there was the conductivity and diffusivity and specific heat, and the quick transient still calculating. So that concludes the demonstration. This is counting down 9 minutes. We'll let this finish, and that will continue on to measure 1, 2, 3, 4, 5, and that data will be available for analysis just like the set we just showed. Thanks for joining. If you have any questions, please get a hold of us. We're happy to answer any questions you may have.